Hi, welcome back to the Electronics channel and part 2 of the DARE amplifier V1100 repair. So last time we managed to get the amplifier running, but we noticed we've got crackly pots, so we need to clean the front channel gain controls. We've got some crackly switches at the back, which seem to be the original problem, or at least the reason there was no sound. We've got a couple of bias adjustment trimmers that potentially need cleaning and certainly readjusting. And then general dust cleaning and tidying up, and we should be complete with this. So I'm going to crack on straight away with starting to clean the controls. So I'll bring out the Super Service Old 10, and I'm going to go straight in for the presets to start with. Let's see if we can. It's going to be tricky to get. Might be tricky to get it inside the preset, but we'll just coat it up and give it a good twiddle. Set it to minimum. Same for the other channel. Okay, we've got the switches on the back panel. It's quite tricky to activate these switches actually, so I think I'm going to have to turn this thing around so that I can get to them. Alright, so we'll give this one a bit of a clean. This was the one that was stopping us getting any audio to start with. Okay, middle position is for stereo. Got the ground lift switch, which we may as well do while we're here. We've got the limiter on-off control. And then we've got the sensitivity adjustment at the end here. And now to get up into these front channel pots, it'd be best if we could turn the whole thing upside down, but there's no access through the bottom, so we have to get creative with the end of this, I think. See if we can convince it to spray upwards. Some kinks in the straw. Hopefully that will work. Yeah, perfect. That should be good. I'll do this one as well. Quite nice, the controls on this are completely flush to the front panel, so although they're a tiny little bit fiddly to use, you know you're not going to break the knobs off with any transportation or anything. Least risk of damage, which is quite neat. Okay. So the other thing that's noticeable is dust on the fan blades here, at least on one side in particular. Now, it's interesting it's on one side in particular because we know this side was over biased, so it's probably running hot. So maybe the fans are independently controlled and this one has been running quite, considerably compared to this one. So it's another indication that the bias has been high on that side. So all I've got here is a nylon brush, which I'm just going to run along the blades just to get that accumulation off on the edge. You always get that build up right on the edge of the blade. Other than that, these fans are pretty clean actually. And I think that's partly down to the drawing from the inside of the box, and there are some mesh filters on the vents that allow the air in. Now these are kind of come unattached now because they're only glued on, so we might go about gluing those back in place, but they may be helping to keep dust out of this thing. It's interesting airflow though, because it's coming in at the sides and out at the back. There's no venting on the front at all, which is unusual. Normally it's front to back or back to front, so that when you put it in a rack, it's either drawing in fresh air from the front or the back. This one's kind of, if you put it in a rack box, it's kind of got the potential to recirculate the air a little bit. So again, thermally, maybe not ideal, but nonetheless, it is what it is. Nothing I can do about that. So this amplifier seems to be quite well built. You know, everything is solid. There's no movement on these heat sinks. This board is solidly mounted. Connectors are all solid. So I don't know how old this is. I'll have a look for a date code, but I don't know how old this is, but it seems to be pretty well built. Very substantial. Massive transformer. It's definitely an old school style amplifier with a big power supply. If it is 1100 watts, then this power supply looks plenty beefy enough to be able to do that. So maybe when we've got this thing up and running and finished, we'll put it on the portable one, the Audio Precision portable one here, see what it actually puts out, and how good the distortion is. And I'll just quickly do the other fan, which is almost clean. Now normally I will take these out and blow them out with the airline as well once they're complete, just to, or normally actually before I do them, but because I've been doing these kind of reveal it on camera videos, I've not been blowing them out beforehand, so I'll certainly go and blow the dust out of this before I put the lid back on. Yeah, because it's always nice to finish the job and get them nice and clean before they either go back to the customer, or in my case, quite often they're for me, and I bought them as repair jobs just to learn more about amplifiers, how they're built, you know, just keep my hand in, as it were. Okay, so I'll just double check the bias pots both set onto minimum. Hopefully minimum is fully that direction, we'll find out in a moment. So what I'm going to do now is power the thing back up. And I'm not going to drive the op amps separately this time, because I'm hoping that with the bias turned down we can get the high voltage rails up high enough that the op amps will be powered by the normal resistor dropper and the Zener regulator bit that they've got in here. So I'm going to disconnect those two op amp supply leads and the ground that went with that. So we'll put our supply back on here. Half amp current limit again. So again, the low voltage stuff is driven by the transformer at the moment, so I'm going to turn on. Yeah, good. So no protect lights. Power lights are on as before. We've got our little MP3 player hooked up. So I'll just get something playing on there, ready for the test. Now I'm going to bring the power supply up. Power supply is on. Okay, current's nice and low now, so those presets obviously are fully anti-clockwise for the minimum bias, which is good. So we've got something playing there. So I'm going to take this up to about 50 volts. That should be enough, hopefully, to get those op amps powered up. Maybe we'll just drop the meter on and check there's enough voltage there. Yes, we've got minus 9 volts. Plus 11.8, so yep, that's certainly powered up now. The current draws at around about 50 milliamps, so it's nice and low. Let's plug the speakers in. Good. Nothing on that channel. Nothing bad on that channel.
Everybody wants your body, so let's check.
Okay, good.
Wake up in the afternoon.
Seems to be working fine.
Cover up the mirror.
No crackles on the pots anymore. Just turn the gain down on the MP3 player a little bit so we can go a bit further. Yep. Clean as a whistle. Okay, all looking good. Now I can see there's separate temperature sensors on each of these heat sinks. There's actually two heat sinks together to form a tunnel here. And there's a sensor on this side and a sensor on this side, so it looks like they're monitoring all four individual heat sinks. Presumably there's some kind of control on the fans, because they're not running at all at the moment. So I'll have to check later when we start getting this thing warm that they are operating properly. Okay, so I think the next thing to do is bring it up on the main supply, I guess. Now I couldn't find a service manual or schematic for this, so I have no idea what the bias current should be set to. So I think the way we'll set that up is to hook it up to the Audio Precision, have a look at the distortion residual. That should show the crossover distortion quite clearly when the bias is on minimum, and then we'll set that for what looks like a nice clean waveform, and then we'll check what current it's drawing to make sure it's not too high and it's not going to be getting really hot. But typically with transistor amps you're looking at about 10-20 milliamps per transistor. Some are less, but that's typical. So I'm looking for about 50 milliamps per output stage here, or about 100 milliamps total. So we might be able to use a clamp meter to check that. So let's get the thing hooked up to the Audio Precision and have a look what the output looks like. Okay, so I've disconnected the power supply now from this, and we're going to go for a full mains power up. So I've reconnected the blue wire from the rectifier that was disconnected when it arrived to me. I've squeezed up the fuse holders ready to take some new fuses. I've got a couple of T10 amp fuses which seem about the right sort of size for the AC side, or well, the DC side of the rectifier, I guess. Now these are prior to the capacitors, so they will be seeing quite high current pulses, so they do need to be a time lag type. And I don't know what the correct value for these will be, but I'm going to put 10s in for now because that's the highest I've got, and they are only 20mm fuses, so I'd be surprised if they were any higher rated than that, because the fuses look a bit flimsy and cheap, to be quite frank. So we're all set, we're all good to go for a full turn on. So fingers crossed, no explosions. Here we go. Okay, no bangs, no protection lights, it's all good. I'm curious to know what the rail voltage on this thing is, so let's check we've actually got good rails and we haven't blown the fuses already. Ground down there, and plus 88 volts there, minus 88 volts there. We'll check our op amp rails. Minus 15, plus 15. Well, there was smoke coming up from somewhere. It smells like hot resistors, so it may just be dust on those power resistors. Let's see if I can see where it's coming from. Okay, what I'm going to do, I'm going to turn off, I'm going to get the thermal camera out and have a look, see what's actually getting hot. I've got my FLIR infracam that I've had for many years. Let's get this started up. Let's wait for it to kick into gear, and then let's just repeat that and see if it is just those power resistors getting hot. If not, then we've got something else to find. Okay, here we go. So it looks like the only thing that's still hot, even though the power's off at the moment, is those resistors, which are kind of hiding behind the wiring loom here. Let's switch back on and see if they're the only thing that's hot. Yeah, they certainly do run hot. We're up to 130, 140 already. 160, 170. Wow. Up to 179, 181. They certainly do run those resistors warm. This one's at 200 degrees. And still climbing. And this one over here. Yep, 205. Still climbing, 220 now. Wow. Well, I know they're power resistors, but I'm not sure I'm particularly comfortable with them running at over 200 degrees Celsius. But I guess that must be how it was intended to be. It is a 230 volt product. And the mains here is probably a little bit high. We can check that on this little meter here. Yeah, it's 247 volts, so it's a little bit high. And the thing is currently drawing 25 watts. But is there anything else hot in this amplifier? There's some little TO220P devices there, plastic package TO220, which are at about 70 degrees. And that one's at 60. The op amps are positively chilling at 39. Nothing else really hot. It's mainly those power resistors, which are now at 240 degrees Celsius. Wow. So the diodes are a bit warm. They're only at about 90 degrees. Got some heat left over in the NTC devices for reducing the main surge, but you can see the relay is on because the relay is actually warm from the operation of the coil. So they should be bypassed, but we can have a check of the volt drop on those just to make sure that that relay is operating. So if we just drop on our AC voltage range here, it looks like these two brown leads coming in are from the power switch, so they must be live and neutral. And then we've got two outputs to the transformer which are duplicated there. So I should, be able to put my probe down into here, compare that to this point here. Yeah, 0. So it looks like that bypass relay is operating correctly. So I think everything looks good. So we'll turn the camera off. Let's have a look about, see if we can check the bias level. So I'll get my DC current clamp out. So we go for the 40 amp DC range. Now this thing drifts a little bit and takes a while to warm up, so we'll zero it. This is the positive supply to this channel. So that suggests 70 milliamps at the moment. Yeah, that's reading 0 there. This should be the same. Yep, give or take. So there's not really a convenient place to put that. Let's maybe clamp around this one and just leave that there for a minute. Check the 0 again. So let's see if this bias adjustment is working. So that 80 milliamps appears to be without bias. There we go. It's increasing now. Okay, so we can read the bias current on there. So I'll turn that down to minimum again. So I've got the audio precision hooked up to the amplifier now. We've got an oscilloscope monitoring the input signal and the residual on the bottom trace. So we should be able to see everything that shouldn't be in the signal will show on the bottom trace. So it's kind of this distortion residual, so it nulls out the sine wave that you're putting in on the top trace and leaves you with everything else, so you can have a close look at the distortion artifacts. I've got a load box up here which we can connect as well. So at the moment it's running with no load, so I'm just going to put a signal on. Turn up the gain. Okay. So getting 5 volts out of the amplifier. Residual looks clean at the moment. A little bit of hum in it, but so let's put a load on this thing. Okay, so I'm going to connect a 4 ohm load to channel 1. There we go. So now we can see the crossover distortion spikes on the trace. Let's bring you in for a closer look. So this is showing the output waveform of the amplifier here. This is the distortion residual, so it's everything in the output waveform that shouldn't be there. So in other words, the fundamental frequency of the sine wave has been taken away and everything that's left is shown magnified here. Both these scales are auto-ranged by the audio precision, so they're not directly comparable, but it gives you a lot of insight into what's going on. So I'm going to get a screwdriver here. I'm going to show you what the effect of the adjusting the bias is. I say this is connected to a 4 ohm load and it's putting out 5 volts at the moment, so it's not doing much power, but you should be able to see as I turn the bias potentiometer up, those spikes should decrease in size. There we go, and eventually they'll blend into the trace just like that. So the slight ripple and whatever you can see on there is just, that's sort of 100 Hz rectification noise that's leaking into the signal somewhere. You quite often see that on amplifiers like this where the wires are travelling all around the case and what have you, because these kind of large currents that are involved in the power supply get induced into the circuit, into the sensitive stuff inside the circuit. So you quite often see that on these amplifiers, but it's at quite a low level. So the distortion now is reading 0.02% at 5 volts out. That's with a bandwidth limit of 22k on the measurement, so we're not looking at any RF noise or anything. So you can see that how that distortion, that crossover distortion, if I just turn the bias down again, you'll see it come back in. So we can set the bias this way. I'd be reasonably happy with that kind of setting there. We can give it some more level and see if it changes much. Okay, we're starting to see a reasonable amount of third harmonic there. Oh, the fan is kicked into action. That's good. Yeah, the heatsink's very warm. I'll turn it down. Oops, wrong control. I'll turn it down in level again. Back down to 5 volts out. So now I think we'll put our clamp meter on. Let's redo our clamp meter. Zero it out. And then we'll check the positive lead here. Now I'm driving current into the load, so we'll see quite a reasonable current here at the moment. 6 out, so let's just turn the signal off for a moment. Yeah, so the bias current for the whole channel is 80 milliamps, so it's actually quite low. As we were seeing on the other side that the current without any bias was about 80 milliamps. So let's see if this side's the same. So I'll make an adjustment here, turn it down to nothing. Okay, that's interesting. On this side it does go down. So about 100 milliamps, which equates to about 20 milliamps per device, which, as I said, is fairly typical for a BJT transistor amplifier like this one. So we'll select for 100. There we go. Just check that that hasn't drifted, because these things do drift this meter. Now let's read the 0. Okay, let's have a look at the other side. Okay, so even with the control on minimum this side, we're seeing a current draw, which is a little bit different to the other side. So let's switch over to looking at the other channel. Channel B, I'm going to put my load, my 4 ohm load onto the other channel as well. Let's turn the signal back on. Okay. Yeah, so with no bias we're seeing the same kind of thing we were on the other channel. Let's turn this control up on this side and see if it disappears like it should. There we go. Disappears into the mains noise that we're picking up. Okay, let's crank up the amplitude on this side. Interestingly, the distortion's not going up on this side. We're delivering 21 volts now. So, what does that equate to? 700 watts. Let's just check we are actually on 4 ohms. We are on 4 ohm reference, that's right. So we're doing 100 watts into 4 ohms with 0.013%. See if I put the 400 Hz high pass filter on to the bandwidth setting here, that removes some of the 100 Hz ripple, makes the trace look a bit cleaner. If I turn it off, it looks like that. Turn it on, it looks like that. And if I trigger the scope on the AC line and back this out, you'll see that let's see if I can improve the way this looks on camera. You see that those bumps, they're the 100 Hz ripple peaks that you can see, and they're stationary now because we're triggering on the mains waveform, so that just proves that they are coming from that source. Okay, let's go back to looking at the waveform. So the fan on this side is kicked in, it's working fine. It's nice and hot. That's good. Okay, so this side's showing 0.013%. Let's turn the signal off. So let's see what the amplifier is capable of outputting. power wise. So single channel driven into 4 ohms. I'm going to run this up, run the amplitude up until distortion reads 1%. At 574 watts on this channel. Let's check the other channel. Swap the mode over. Yeah, this channel's behaving quite differently. Only 443 watts on this channel. You can see it seems to be the negative for the waveform that's getting clipped first before the positive starts clipping. So we compare that to the other channel. Let's swap over to the channel, onto the other channel. On this side, yeah, it's still the negative side that clips first. We're getting 540 watts. It's interesting that the negative is clipping earlier.